equations of two intersecting lines, note that that is in bold font, that's going to be important later on, are given as shown, where a is a constant, and we're asked to find a vector b which is perpendicular to both lines. So let's say the origin is here. Now that minus 12a minus 1 actually gets us onto the line, and then the 2, 2, 1 is the direction vector that takes us to where we want to go. We times by a scalar quantity because that then tells us like how many times of lots of 2, 2, 1 we want to go. Then we can end up anywhere along the line, such as here. Now the other line we're going to get onto is, say, I don't know, over here. That's going to be my 2, 0, 5. And then I'm going to again go along. I'm going to do it in red again to highlight this is then the direction vector, minus 3, 1, minus 1. And that will take me anywhere I want to along the line. And essentially these direction vectors are the direction of the line. The other vectors are just getting us from the origin onto the line. Which means if I want to find a vector b, which is perpendicular to both lines, I need to find a vector that's perpendicular to this direction vector and to this direction vector. The rest is irrelevant. For this, I can use the vector product. B is going to be, we can write it as a determinant, I, j, k are 3D vectors, and then I'll just put in 2, 2, 1, that first direction vector, okay, along the second row, and then minus 3, 1, minus 1. This will necessarily give me a vector that's perpendicular to both lines. I'm not proving it here, but it is necessarily true and something to remember. Can expand that determinant along the first row, so I get I times 2, 1, 1 minus 1, and I get minus j, because it's second row, first column, becomes a minus 1 to the power of 3, and then I get 2, 1, minus 3, minus 1, then plus k, 2, 2, minus 3, let me do that again, minus 3, 1. Okay, let's deal with these determinants. We've got minus 2, minus 1, so it's minus 3i. I've got minus 2 plus 3, which gives me 1, but then I make it minus, so I got minus j, and then 2 minus minus 6 becomes plus 8k. Therefore, b is equal, I could leave it like that, or I'm going to write it as minus 3 minus 1, 8. All right, the next question caught me off guard a little bit. I had to think about this a lot. Show that the dot product between b and actually it's this position vector and b and this position vector are equal. Now what you can't do is just start expanding the dot product, because that's not showing that they're equal necessarily. That's like solving it. And you're going to get one of them in terms of A and one of them not. That's actually what we're going to do in part C to solve them to find A. We have to show where this comes from, and it's where the intersecting lines part comes in. So when the lines intersect, it must be that minus 12a minus 1 plus lambda times 2, 2, 1 is equal to 2, 0, 5 plus mu minus 3. Now you could go ahead and solve this, but you don't need to. It's only a couple of marks here. But we know this is an equation now, so I'm going to take the dot product with b. So b dotted with all of this, and I think I'm just going to go straight to it. I can actually just, if I can expand it like I would a bracket, do the dot product of b with the first vector and then with the second vector. Oh, this is why you really should underline your vectors, because it really makes clear what's a scalar and what's a vector. Now, we've just found, so B perpendicular to 2, 2, 1, and minus 3, 1, 1. We got this from part A. So B dotted with 2, 2, 1, and B dotted with minus 3, 1, minus 1 is equal to 0. Because remember, it's going to be cos of the angle between them, and that's 90. Cos 90. I don't know how much to, it's only a couple marks, but I just want to explain my work. And so actually these just go. And that leads us to the result that we wanted. Therefore, B dotted with minus 12, A minus 1 must equal B dotted 205. I got to be honest, when I did this question, I went ahead and expanded the dot product, and then I realized, oh, you know what, I'm doing part C. So if you do it in a different order, don't worry about it. But this is what we've got to do now. Okay, so remember, I know what B is, in fact. I can just sub in. We've got our minus 3, minus 1, 8. But it's got to be said, actually, they're kind of hinting at a general result here. This would be true for any pair of intersecting lines. You could create, this perpendicular vector, and it will necessarily be true that that perpendicular vector dotted with each of the position vectors would equal one another. It's not just true here, this will always be true for two lines that intersect. They must intersect. Okay, now I can expand using the dot products. We've got 36 minus a, just the x components, and then the y components, and then the z components. That must equal minus 6 plus 40. So 28 minus a is equal to 34. A is going to equal minus 6. Okay, nice question here. It kind of started out quite standard, really. Maybe that's what you're looking for, just a perpendicular to both lines, determinant bit. Solving an equation for C was okay. B was the really interesting bit, I think. So I've learned something from this question, and I hope you have too. Well done.